In this video, we're going to learn about exponential graphs. One interesting thing about exponential graphs is that their growth can be quite rapid. They often start slowly, but then eventually shoot upward. This rapid acceleration has wide-ranging implications in scenarios such as compound interest, population growth, and even the spread of diseases. Let's start by graphing y equals 2 to the x power using a table. When x equals 3, y will equal 2 to the third power. When x equals 2, y equals 2 to the second power. Remember that anything to the 0 power equals 1, and negative exponents have nothing to do with negative numbers. They have to do with fractions and things being in the wrong place. So here this 2 to the first power needs to be in the denominator. So 2 to the negative first power equals 1/2. 2 to the negative second power equals 1 over 2 squared, which equals 1/4. And 2 to the negative third power equals 1 over 2 to the third power, which equals 1/8. Each row in the table represents a point. I'm going to start at the bottom of the table on the left. Those points are very close to 0, but as we move to the right, the graph starts to shoot upward. Now we notice this graph shoots rapidly upward as we go to the right. Now, as we go to the left on the graph, the curve is approaching the x-axis. But if we look at the pattern here, we notice that these y's will never get negative. They're just going to get closer and closer and closer to 0. So this graph actually never crosses the x-axis. So with exponential graphs, it's important that we never let them cross into regions that they're never going to get to. Now, a couple of things about this before we move on. Notice that when x equals 0, whatever the base number is going to equal 1, because anything to the 0 power equals 1. So even if this had been y equals 17 to the power of x, the point 0, 1 would still be on the graph. So when x equals 0, that's a very helpful point for our graphs. Another helpful point is when x equals 1. We raise that coefficient to the first power, which always equals that coefficient. So we'll be using these 2 points to help us graph our exponential graphs. Right here we have 1/2 to the power of x. So 1/2 to the third power, that would be 1/2 times 1/2 times 1/2, or 1/8, which was 0.125. And then here we have 1/2 times 1/2, which is 1/4. And here we have 1/2 to the first power, 1/2 to the 0 power. Anything to the 0 power equals 1. 1/2 to the negative first power? Well, that negative exponent means that 2 is in the wrong place in the fraction. So this is actually equal to the first power, which equals 2. 1/2 to the negative second power, that's the same thing as 2 squared, because that negative exponent means that the 2 is in the wrong place in the fraction. Very similar numbers to our previous graph. They're going to appear just a little bit different in this graph over here. This time, the small decimal numbers are on the right side. So when x is 3, y is pretty close to 0, but not quite 0. When x is 2, y is still pretty close to 0. When x is 1, y equals 1/2. So we're still only halfway to 1. Then finally, when x equals 0, y equals 1. And finally, when x equals -1, we go up to 2. and then up to 4, and then up to 8. Comparing this graph to the previous one, this new graph is a reflection, a horizontal reflection over the y-axis of our previous graph. The previous graph was y equals 2 to the x, and the graph of y equals 1/2 to the x is just the reflection of that. Now that actually makes sense, because y equals 1/2 to the x power is actually the same thing as y equals 2 to the negative x power. That negative exponent just means the 2's in the wrong place, and so it ends up in the denominator. Let's use some of the clues we learned about in the previous graphs to graph two more parent graphs. So for y equals 3 to the power of x, well, when x is 0, y is going to equal 1, because anything to the 0 power equals 1. When x equals 1, then y will equal 3. When x equals 2, y equals 9, because 3 to the second power equals 9. And that's about all the space we have in the upward direction. Now x to the negative first power, well, that would equal 1/3. So already at -1, we're down really close to 0. But remember, as x gets more negative, y is never going to be negative for this particular equation. It'll just get closer and closer to 0. So for y equals 3 to the power of x, this graph shoots upward rapidly as we move to the right. Now this will be the same exact graph, just reflected across the y-axis. Let's take a moment to figure out the domain and range of these two graphs. The domain, those are the x values that this graph uses, and it's going to go all the way to the left and all the way to the right. So x is in between negative infinity and positive infinity. We could read this: negative infinity is less than x, which is less than positive infinity. Another way to write this is we could say all real numbers. Now the range, this graph never goes below the x-axis, because as x gets more and more negative, y is going to get closer and closer to 0, but it's never actually going to get negative, because negative exponents don't have anything to do with the negative numbers. So we could say y is greater than 0. The domain, once again, those are the x values this graph uses, and same thing, it's going to go all the way to the right and all the way to the left. X is in between negative infinity and positive infinity, or all real numbers. And the range, once again, those are the y values this graph uses. And the y's have to be greater than 0, because no matter what x equals, y will always be positive in this case. Now the parent graph for this particular equation is y equals 1/2 to the x power. But now we're subtracting 4. So all we need to do here is take the graph of y equals 1/2 to the power of x and move it down 4. So the parent graph, that went through the point 0, 1 and -1, 2. And as we move from left to right, it approached the x-axis. Well, that's the parent graph. We're going to move it down 4. So let's take this point and just count down 4. 1, 2, 3, 4. Same thing with this point. Let's move it down 4. And then the line that we're not going to cross, that's now going to be here at -4. So we'll have the graph shoot up to the left and never cross y equals -4. And there's our sketch of y equals 1/2 to the power of x minus 4. The domain on this graph, once again, all real numbers. And the range, the y values this graph uses are the y's greater than -4. Now here we are subtracting 4 inside the exponent. And what this is going to do is move that graph right 4. So notice when we subtracted a number after the exponential term, it works just like our common sense would like it to work. -4 was down 4. But here, inside the exponent, it's kind of backwards. -4 is right 4. So the parent graph for this equation is y equals 3 to the x, and that will go through the point 0, 1, and also 1, 3. And it shoots up to the right and never crosses the x-axis. Well, this graph is going to be the same. It's just 4 units to the right. So I'll take these 2 points and move them to the right 4. Like so, and it shoots up to the right and never crosses the x-axis still. And the x values this graph uses are all real numbers. So x will be in between negative infinity and positive infinity. And the y values this graph uses are the y is greater than 0. So the range is y is greater than 0. Here we're going to make reflections. Y equals -3 to the power of x. Well, that's going to be related to the graph of y equals 3 to the x power. But all of the y's will be negative instead of positive. So first let's graph the parent graph. That will go through the point 0, 1 and 1, 3. This is the parent graph, not the actual graph for this example. So we're going to change the sign of all the y values of these points. So for this graph here, instead of going through 0, 1, it's going to go through 0, -1. And for this point, instead of going through 1, +3, this graph will go through 1, -3. So our graph for y equals -3 to the power of x will be a reflection of its parent graph over the x-axis. And this graph uses all real numbers for its x values. And the range, it uses all the negative numbers for its y's. So we can say y is less than 0. This graph will have the same parent graph. So let's make a sketch of y equals 3 to the power of x first, and then we'll see what kind of reflection the graph of y equals 3 to the negative power of x equals. So here's the parent graph. It goes through 0, 1, because 3 to the 0 power equals 1. And 3 to the first power is 3, so it'll go through 1, 3. Shoots up to the right, gets closer and closer and closer to 0 as it moves to the left. That's the parent graph. Now, y equals 3 to the negative x power is the same thing as y equals 1/3 to the x power. Because that negative exponent just means the 3 is in the wrong place. We need to move it to the denominator. And when our base is less than 1, that's when it shoots up to the left. So it'll still go through the point 0, 1, but instead of going through the point 1, 3, it's going to go through the point -1, 3. And it's going to shoot up to the left and get closer and closer and closer to 0 as it moves to the right. And there's our graph of y equals 3 to the negative x power. So the domain is all real numbers. Those are the x values this graph uses. And the range are all y's greater than 0. Let's write equations for these two graphs. Right, we notice this graph goes to the point 0, 1, and it's shooting up to the left. So let's look at the point with an x-coordinate of -1. It goes to the point -1, 3. That's going to be y equals 3 to the power of negative x. And if we want to write that without a negative exponent, it would be y equals 1/3 to the power of x. So if your graph is shooting up to the left, you're going to have a fraction less than 1 being raised to the power of x. And to figure out what the denominator of the fraction is, we'll just look at that first point when x equals negative 1. Well, over here, we notice it goes through the point 0, 1, but then it goes through the point 1, 3. Well, since this graph is shooting up to the right, we're going to have a number greater than 1 being raised to the power of x. And since it goes to the point 1, 3, it'll be 3 to the power of x. I hope these examples about graphing exponential equations have been helpful. This is Mr. Ela, signing off.